So welcome back. All right, we're going to finish off section 7.3. So section 7.3, what we were doing last time was we were evaluating these integrals that needed some sort of substitution in order to get these answers. All right, so what we want to do, some sort of trigonometric substitution. So what we want to do at this point in time is we want to keep working with this, but we want to make this a little bit more challenging. So let's start with part A on this example for this evaluate, and these are going to be a little bit more challenging. So this is going to be the integral from 0 to 1 for the integrand of square root of x squared plus 1 dx. All right, so we then need to figure out what substitution we need to make here in order to make our lives easier. Now, the substitution that we're going to make at this point in time will be the substitution. If we go back to the table that we were looking at, we're going to make a substitution that x is going to be equal to tangent of theta. All right, and that's again because we see some x squared plus some other squared value. If this is the case, then our dx will be the derivative of tangent, which naturally should be secant squared theta d theta. Nice. So again, restriction values, theta must be between negative pi halves and pi halves. Very nice. All right. Now that we have this, we're going to go through and we're going to try to evaluate this integral. It's going to be the integral of the x value, that's just going to be tangent squared theta plus 1. Our dx turns into secant squared theta d theta. Limits of integration time. All right, limits of integration here. X is 0. If x is equal to 0, then we get 0 is equal to tangent of theta, which naturally means that theta must be 0 according to our restrictions. And if x is equal to 1, then we naturally get 1 is equal to tangent of theta. And as you saw with the last problem, tangent of theta is equal to 1 only at pi fourths for that interval restriction. Nice. So we have these. Now all we have to do is keep going. All right, easier said than done. All right, give me one quick second. Let me, bam, look at that. Isn't that awesome? I know there's a way to copy and paste here, but bear with me, I'm learning. All right, that was 0 to pi fourths. Now look at the radicand. The radicand there should remind you of a Pythagorean identity. And you'd be right, it is a Pythagorean identity of square root of secant squared. Because that's a Pythagorean identity of square root of secant squared, we're going to be able to look at secant of theta multiplied by secant squared theta d theta. Very nice. Now, some of you might say, yeah, Mr. Castro, I see that's going to be secant cube theta, and that's awesome. You're absolutely right. If you want to go ahead and multiply those two, you're more than welcome to do so. However, for the purposes of this problem, it's actually going to get a little bit more messy if we do that. So I want to keep them as they are right now. And what I want to do is I want to approach, or I want to integrate using by parts. So I'm going to use by parts integration. So let's see if we can use our by parts integration at this time. All right, let's see how this is going to work out. All right, let's scoot up just a little bit more. Here we go. All right, so I'm going to let my u equal to secant of theta. Therefore, du is, yep, you guessed it, secant theta, tangent theta, d theta. And if u was secant of theta, then that means my dv must be secant squared theta d theta. And I'm going to ask you really quickly, what is the antiderivative of secant squared theta? All right. Yeah, I know. I wish I was a question on Who Wants to Be a Millionaire. I'd be a millionaire right now. Unfortunately, that's not the case. So, antiderivative of secant squared theta is, you guessed it, tangent of theta. Look at that, real nice. Integration by parts means that we're going to do the integral of u times v minus the integral, or excuse me, the product of u times v minus the integral of v du. So u times v, that is secant of theta multiplied by tangent of theta, evaluated by the limits of integration 0 to pi fourths minus the integral, ooh, what's that there? The integral from 0 to pi fourths of v du. Now v du turns out to be secant of theta, tangent of theta, multiplied by tangent of theta d theta. Wow, that's rough. All right, so let's see if we can go through and feng shui some stuff. So secant of theta times tangent of theta, that's going to be from 0 to pi fourths, minus, would you agree that's tan squared? Nice, because I would. So that's secant of theta multiplied by tangent squared theta d theta. Now, you might say to yourself, I made a substitution, or I went through by parts and I didn't get anywhere. You betrayed me, right? And, you know, you're going to be at a battle with yourself, but it's going to be okay. It's going to be okay. Now, if you did do that, it's okay, because there is always a solution to the mistakes that were made, or in this case, not a mistake that we made, because we know tangent squared theta, that's a Pythagorean identity. If we go back to the Pythagorean identity of 1 plus tan squared theta, this is equal to secant squared theta. But tangent squared theta is equal to secant squared theta minus 1. Ooh, look at that. Doesn't that give you chills? That gives me chills. All right. All right, so secant theta, tangent theta, evaluated from 0 to pi fourths, minus 0 to pi fourths of secant cubed theta minus secant theta d theta. Look at that. Now, you might say, Mr. Castro, we doubted ourselves and you said this was going to get easier, and now looking at this integrand, it doesn't look much easier. And you're absolutely right. It does not look much easier. But I want you to sit back really quickly. Ooh, let's try this one. I want you to sit back really quickly, and I want to see this. Does this piece of information right here equal this piece here? So I'm going to let you think about that. Both integrands are from 0 to 4. Sorry, both integrals are from 0 to pi fourths. Both of the integrands are going to be secant cubed. So naturally, we're going to arrive at this other conclusion. All right, I'm going to keep bringing all those work down here. I know these problems are really long. That's why I chose to break it down into 2 videos. Which means we had the integral from 0 to pi fourths of secant cubed theta d theta, and that was that left-hand side here. All right, that was this left-hand side that we were using here. All right, now let's grab the right-hand side. The right-hand side was secant of theta multiplied by tangent of theta evaluated from 0 to pi fourths minus, I'm going to break up that integral. That's going to be 0 to pi fourths multiplied by secant cubed theta d theta, distribute the negative, and that's going to be positive for the integral from 0 to pi fourths for secant of theta d theta. Now, the important part that I wanted you to see a little while ago is this, that this integral and this integral are exactly the same. And because the integrals are exactly the same, we can add the integral on the right-hand side of this equation to the left-hand side. In doing so, we are now left with 2 times the integral of 0 to pi fourths of secant cubed theta d theta. And what we have is the right-hand side being equal to this result. 0 to pi fourths for secant of theta d theta. Look at that. Wow, that is a beautiful result. I know we might have different definitions of beautiful, but that is spectacular right there. Now, once we have this, we're then going to go back and we're going to try to say, okay, well, let's evaluate what is secant of theta. Now, again, that secant of theta we went through in the previous example that we could evaluate that. So, when we're working with this, we get secant cubed theta d theta is equal to, this is going to be 1/2 multiplied by secant theta tangent of theta. Yes, it's going to be evaluated from 0 to pi fourths, but so is this integral. So I'm going to wait on that, and that's going to be plus the natural log of secant theta plus tangent theta. And this is all being evaluated from 0 to pi fourths. Which means, let's evaluate. Secant pi fourths multiplied by tangent pi fourths plus natural log of the absolute value secant pi fourths plus tangent pi fourths minus secant at 0 times tangent at 0 minus natural log of the absolute value of secant at 0 plus tangent at 0. Here we go. Let the party begin. All right, secant at pi fourths. Secant at pi fourths would be root 2. Tangent at pi fourths, that would just be 1, plus natural log secant at pi fourths, again, that's just root 2. Tangent at pi fourths, that's 1. Minus secant at 0, that's 1, but tangent at 0, that's 0, so that kind of goes away. And then we're left with natural log of secant at 0, that's 1, tangent at 0, that's 0, so that's going to be the natural log of 1. But natural log at 1, you all know to be 0. Which means this integral actually just evaluates to be this really nice root 2 over 2 plus 1/2 multiplied by natural log of square root of 2 plus 1. Look at that. Wow. That is beautiful. Beautiful, beautiful. But again, at the end of the day, look at all of the work that went into this integral. It didn't look like it was going to be very tough at the beginning. But again, with the whole substitution process we went through, and we actually get to find out what is that value for that integral. All right, nice. So we're going to work on the next example, and this next example is actually going to be the last example for this section. So this is going to be part B for this extremely hard problem set that we're working with. Here we go. So this is going to be the integral of x squared divided by square root of 3 plus 4x minus 4x squared, and that's going to be cubed. And that's all inside of this square root. This is all dx. All right. So I want you to take a few seconds and I want you to look at this integral. Try not to be intimidated by it, because it can be very, very intimidating. But I want you to try to look at this with the lens that we have to make a substitution and that we have to make some sort of trigonometric substitution. All right, so I want you to look at it for a minute and try to see if we can have a few methods of approach. All right, so here we go. Thoughts, thoughts, thoughts. All right, so the first thought that comes to mind is that this is not in any form that we saw before. So what we're going to have to do here is we're going to have to complete the square. So let me write that here. Let's complete the square. Complete the square. And we're going to complete the square on that denominator. Now, I'm going to tell you this, that for all of the times that I've taught calc for a very long time, completing the square is one of these processes that a lot of students tend to forget, but it's very, very beneficial. So here I'm going to have a -4. I'm going to factor that out. So that's going to be x squared minus x. And then I still have a +3. And then all of that is raised to the power of 3/2. And that's all dx. Perfect. All right. Completing the square process, we're going to take that b coefficient. We're going to divide it by 2, and then we're going to square that result. Therefore, we get x squared minus x, and here is what we are adding in. We are adding in, let me go in red here, we're adding in positive 1/4 and negative 1/4. Now, if you look at that, all we're doing is we're saying there is a 0 that exists right in here. So I'm going to manipulate that 0 to be 1/4 minus 1/4. In doing so, I'm going to group these first 3 terms, and by grouping those first 3 terms, I am now going to be able to factor it out perfectly. So that's going to be x squared divided by, oh, you know what? I don't like that divided by symbol there, so let's go x squared divided by, here we go, -4 multiplied by x minus 1/2 quantity squared, but then the -4 is going to multiply this -1/4 to give us a +1, and then we have +3 raised to the power of 3/2. And this is all dx. All right, let's keep working with this. Now, with this whole process, this is really nice now, because I want you to look at this. This is now going to be, let me rewrite this, 4 minus 4 times x minus 1/2 to the power of 1/2, and this is all raised to the power of 3/2. And that's all dx. So let's pay attention to that denominator. Looking at that denominator there, oops, let me move this over, here we go. So looking at that denominator there, I see that I have a 4, so I'm going to go ahead and factor out that 4 from that denominator. And when I factor out that 4, it's going to be 4 to the power of 3/2, and then I'm still going to have in here 1 minus x minus 1/2 squared to the power of 3/2, and that's in the denominator where x squared is in that numerator. So you can go through the whole process and say that 4 to the power of 3/2, that's really just the square root of 4 raised to the power of 3, but the square root of 4 is 2, so it's really just 2 to the power of 3, and 2 to the power of 3, I have my daughter here, what's 2 times 2 times 2? 8! Wow, look at that. Wow. All right. So here, that's just 8 multiplied by 1 minus x minus 1/2 squared to the power of 3/2, and that's all dx. Look at that. That is looking promising. So what I want to do at this point in time is I need some substitution at this point in time. Now, would you agree that my perfect square, and the perfect square that I'm looking at is right in here, that this perfect square is not necessarily in the substitution form that we want. However, we can get it there. What I'm going to do at this point in time is I'm going to say let 2x minus 1 equal to 2 sine theta. And you might say, Mr. Castro, where are you coming up with these numbers? Well, I want you to look at the perfect square right in here. Could I write that factor as 2x minus 1? Sure we can, if we went ahead and accounted for that 1/2. Now, because we're saying 2x minus 1, that's where this appears here. Now, making this substitution is going to be very, very beneficial. So, what I'm really quickly going to do is I'm going to solve for x. X is 2 sine theta plus 1 divided by 2. And the reason I wanted to solve for x is because now when I do my dx, I can now see that dx will just be cosine theta, d theta. Look at that. Beautiful. And I say that's beautiful because now my numerator, look at that numerator. That numerator is now going to be sine theta plus 1/2 raised to the power of 2. That's x, right? X squared. All divided by that 1/8. I'm going to factor out to the front of that integrand or integral. So that denominator is now going to be something nice that we want to see. 1 minus that x value is now sine theta plus 1/2 minus 1/2 squared raised to the power of 3/2. Oops, let me write that a little bit neater here. A little bit more neat. So 3/2, there we go. Now I'm really quickly going to say that this here was my x value. This was a substitution that was made. All right, so the substitution that was made, and I'm still missing one part because I'm missing my differential. My differential is going to be cosine theta d theta. Awesome. So let's go through now. Numerator, there's no way around it. It's going to be nasty. It's going to be rough. So for the numerator, I'm just going to kind of keep it there like that for now. So keeping it like that for right now. I'm going to say this is now sine theta plus 1/2 raised to the power of 2 multiplied by cosine theta d theta, all divided by, let's look at that denominator. That denominator, sine theta plus 1/2 minus 1/2, the halves cancel, and we're just left with 1 minus, what's that going to be, sine squared theta raised to the power of 3/2. Now I'm going to ask you guys, what's 1 minus sine squared? Well, 1 minus sine squared, you guessed it, Pythagorean identity. Man, those Pythagorean identities are everywhere. But they're nice because they're kind of like lifesavers here. Ooh, speaking of lifesavers, I could go for a lifesaver candy. But I don't want to go out to the store right now, so that's okay. So let's see, cosine squared to the power of 3/2. So cosine squared to the power of 3/2, that's going to be the square root of cosine squared. Again, paying attention to the restrictions, we should be good. So this is now going to be cosine raised to the power of 3. So that's 1/8 multiplied by the integral of sine theta plus 1/2 squared times cosine theta, all divided by cosine to the power of 3 theta d theta. Nice. So looking at this here, we now have this really nice place where we want to be at. All right. I'm going to go ahead and I'm going to rewrite this down here just for continuity here. So this is going to be, was that sine theta plus 1/2 raised to the power of 2. Oops, there we go. Now the cosines, one of them is going to cancel, so we're going to get cosine squared theta d theta. Boom. Nice. Now using this, I'm going to rewrite this really quickly. I'm going to use some algebra work here. So would you agree that this is just sine theta plus 1/2 divided by cosine theta, where all of this is raised to the power of 2? All right, let that process in for a little bit, and it should be correct. Now, this is all going to be 1/8 multiplied by the integral of sine theta divided by cosine theta. Oops, excuse me, cosine theta plus 1/2 cosine theta, and this is all raised to the power of 2 d theta. And the reason I wanted to do that is because I want to move away from the fractions, and if I can move away from the fractions and make something more beneficial happen, then hey, more props to us, because we found what we were looking for. All right, look at that. So now we have this binomial here raised to the power of 2. So we can go through and we can use our expansion using distribution. So this is going to be 1/8 multiplied by the integral of tangent squared theta plus tangent theta secant theta plus 1/4 secant squared theta. Nice. Look at that. That's really good. So now we're at this point in time. So what we want to do here is we can try to integrate term by term. Now, I want you to pause really quickly. All right. So if you want to pause this video, go ahead and pause this video. But before you do, I want you to think about this. Is there some way, or let me actually scratch that. Can we find the antiderivative for tangent theta secant theta? And the answer should be yes. The antiderivative is just secant. Nice. Do we have an antiderivative for secant squared? Let's think about that. All right. The answer should be yes. We do have an antiderivative for secant squared. That's just tangent. So looking at these two terms, we know those antiderivatives. The only antiderivative that we don't know is the last antiderivative here for tangent squared. We don't have one there. So what to do? Well, there's this really nice thing that we could do. We can make a substitution by using one of our Pythagorean identities. If we use a Pythagorean identity that 1 plus tangent squared theta is equal to secant squared theta, then we actually avoid that whole process and we actually get everything in terms of secant squared theta. Now let's keep working up here. Look at that. That's going to be 1/8 multiplied by how many secant squareds do we have? One of them's 1/4, the other one's 1, so 1/4 plus 1, that should be 5/4. So we have 5/4 secant squared theta plus tangent theta secant theta d theta. Oh, sorry. And we still have a -1. Excuse me there. Wow. Look at that. So -1 d theta. That's perfect. That is gorgeous right there. Now all we have to do is integrate term by term. And because we already know these antiderivatives, we don't need to go through and play around with substitutions or anything like that. So, what's the antiderivative for secant squared? That's just tangent of theta. What's the antiderivative for tangent secant theta? That's just secant theta. What's the antiderivative for 1 with respect to theta? That's just theta. You guessed it. So now we're here. Awesome. And again, this is where we want to be. So let's go through and let's distribute that 1/8. I don't like that 1/8 just floating around up there. So I'm going to distribute my 8. So this is now going to be 5/32 multiplied by tangent of theta plus 1/8 multiplied by secant of theta minus 1/8 theta plus c. Now again, keep your eye on the prize. Are we solving for theta when we're working with this integral? And the answer is no. We are not solving for theta. Looking at the initial integral, we are trying to solve for x. So when we're trying to solve for x, we have to go back and we now have to reinterpret all of this in terms of x. So we have to now go through and make those resubstitutions. We got to find out what theta is and what tangent of theta and what secant of theta are. So remember, the substitution that we initially gave was that 2x minus 1 was equal to 2 times sine of theta. When we solved for x, x was equal to 2 sine theta plus 1 divided by 2. Now, I'm actually going to do something really quickly. All right? The thing that I'm going to do really quickly is I'm going to take this substitution that we have here, and I'm going to solve for sine of theta. Sine of theta is really just 2x minus 1 divided by 2. Why did I want to do that? Well, I wanted to do that specifically because if sine of theta is some angle measurement that I'm looking at here, then the ratio given is the opposite over adjacent, which means I'm able to solve for this missing side. So the big question is, what is that missing side? Well, we can use a Pythagorean identity or the Pythagorean theorem. Pythagorean theorem would then let us know that this missing side is 4 minus 2x minus 1 squared. Now, why did I want to do all of this? Well, I wanted to do all of this so that I can find what was that answer that I need. So here we go. That answer, back to the answer, 5 over 32, tangent of theta. So let's look at this angle here. Tangent of theta. Tangent is opposite over adjacent. So this is now 2x minus 1 over square root of 4 minus 2x minus 1 quantity squared. That's tangent. Plus 1/8 multiplied by secant of theta. Secant of theta is just the reciprocal of cosine. Cosine is adjacent over hypotenuse. So let's take the reciprocal of that. That's going to be 2 divided by square root of 4 minus 2x minus 1 squared. So there's secant. Minus 1/8 multiplied by theta. So the big question is, what is theta? Well, theta, if we go through and if we solve here for theta, taking the inverse, then we're going to get 1/8 multiplied by sine inverse of 2x minus 1 over 2. And then naturally we just need the constant, plus c. Wow, look at that. That looks awesome so far. Let's go through and I see some items that can be simplified. So really quickly, I'm going to go through and simplify some of these items. I'm going to highlight these items that we can simplify here. Notice we have two fractions that we're trying to add together, so I believe we can add those two together quite easily. All right, let's multiply the 5 in that numerator, so that's going to be 10x minus 5 divided by 32 multiplied by 4 minus 2x minus 1 squared, plus this denominator doesn't have a 32, so I'm going to multiply by 4, both numerator and denominator, so that's going to be 8 over 32 multiplied by the same denominator. In other words, we have an LCD. Nice. All right. Minus, that's then going to be 1/8 multiplied by sine inverse of 2x minus 1 all divided by 2, and that's plus c. Almost done. Almost done. Hang with me, people. Hang with me. All right. Hang in there. Hang in there. All right. So 10x minus 5 plus 8, that's going to get me 10x plus 3 all divided by 32 multiplied by my radicand, 4 minus 2x minus 1 squared, nice, minus 1/8 multiplied by sine inverse of 2x minus 1 all divided by 2 and then plus c. Bam! Look at that. That is amazing. That is the answer that we want to see, that I want to see. All right. So I hope this problem was not too intimidating. Again, there will be some sort of a problem like this on your exam. I'm thinking exams are going to be sort of a take-home style of exams. So you're going to have a lot of items at your disposal, but any work that you show or that you turn into me must be your own work. So I hope this helps, and I will see you all next time for section 7.4. Auf Wiedersehen.